Today I'll be presenting on my paper, MoLEx, Mixture of Layer Experts for Fine-Tuning with Sparse Upcycling. So this is a paper that I wrote with my advisor, Professor Tan from NUS, and yeah, so we're from Singapore. Okay, so first let's start off with a little bit of background, but I think I'll try not to spend too much time on it as I think I don't have much time to speak. So I think everyone is also very familiar with Sparse Mixture of Experts, where basically we have an MoE layer where each example is acted on by a subset of the parameters, and each expert focuses on predicting the right answer for a subset of cases. So you can see here that we will have a gating network that will send our input to either 1, 2, or k experts, and we finally recombine the output from each expert to send to the following layer. And why is the advantage of this? Is because there is a degree of sparsity that decouples the parameter count from the compute per example. So this allows us to have extremely large but efficient models. And the citation is at the bottom here. So I just want to focus a little bit on the gating network, which is the router, because this is something that we will also implement in our method. So basically we represent the router by G, and for each input to the layer xt, we have a linear gating network, which is wxt plus b, so there's a little bias there. And each gi from 1 to e, and e is the total number of experts, represents the affinity scores between the input and each expert. And so how do we choose which expert to use or which expert to route to? We basically take a top k, which is the k maximum values out of this vector g, and then we do a softmax to have a linear combination of the outputs of each expert. So ui here is the expert. Alright, so how does this relate to MoLEx? So basically our mixture of layer experts model, which is like MoLEx, MoLEx, recycles all the pre-trained layers as the experts. So instead of creating new experts in each layer, we basically used a pre-trained model to, and each layer in that pre-trained model will represent one expert. And we have a router that will route our input to each layer to an expert, which is just another layer in the whole model. Okay, it sounds a bit convoluted, but let me just explain. So basically we have the input to the first layer, U1, and this is Z1. And so Z1 will be processed by layer U1, and the output is U1, Z1 here. And then we will also route Z1 to the router, and our router will choose one expert, and an expert is basically just one layer in the pre-trained model. So in this example, our input has chosen UT minus 1, which is the last layer in the model. And so we will route our input to UT minus 1, take the output, and linearly combine that with the output from the first layer. So basically, we linearly combine it using a weight alpha here. And then we send this as Z2 to the next layer, and we do the same thing all over again. So the input to U2 is processed by U2, and then also sent to a router, and then we choose another layer as an expert, and then we linearly recombine. So at every layer, we are doing this. So you can just imagine when we do mixture experts, we kind of have experts expanded horizontally in the model, but now instead of doing it horizontally, we do it vertically. So we just make it perpendicular. Yeah. Okay. And yeah, so this is our model. And our motivation for this is that we can view each layer in a pre-trained model as an expert in extracting distinct linguistic features. So I'm not sure if you're familiar with this paper on BERT, where someone did a probing experiment where we find that each layer actually can extract different types of linguistic features, for example, grammar or tenses or syntax. Yeah. So basically what we do is that we view each layer as an expert in extracting these kinds of different linguistic features. And by facilitating this kind of interlayer information exchange, MoLEx actually enhances a model's performance while minimizing the total parameter count, because we do not have to duplicate all the different experts. And so our method is quite simple, and we are able to provide also another simple theoretical analysis on it. So basically, we want to view MoLEx as an ensemble model. And we only do this in a simple case where each layer is a linear layer, which is basically just an MLP. And how we do this is that we unroll the input to each layer, which is ZT. And you can see here, it's ZT minus 1 plus alpha, UT minus 1, and so on. And UIT here is the layer chosen by the router when we send our input ZT to the router. And so because of the linearity of UJ, we basically can rewrite this as a composition of UJ and UT minus 1. And so if we continue to unroll this, we can actually find this expression at the bottom here, where we have a weight, C, I0, I1, and so on. And this weight is basically just to represent all of the alpha, or 1 minus alpha, alpha 1 minus alpha, depending on the layer that is chosen by the router, and the compositions of all the layers chosen by the router as well. So I0, I1, and so on is such a mouthful and it's so complicated. So we just kind of relabel it to J here. And so we can write this as a simple expression here on the right. All right, so now in doing all of this, our aim is to show that MoLEx will be a more robust model because it's an ensemble. And I think this is also quite an intuitive understanding because an ensemble models should be more robust than just like a single model. So basically, we first define what is robustness. And okay, so this seems kind of complicated, but actually it's really simple. So basically, if we have a classifier model that outputs like the class that we would like to classify our input, and we have an input X, and we basically perturb it within a epsilon ball with a radius of epsilon and a center X. So basically, you just move X to like X plus epsilon, and we define robustness as the output is the fact that the output from the classifier model does not change. And so in this way, we say that F is actually epsilon robust at X. And we have a little theorem here that will set up the next slide to show that MoLEx is more robust than just a regular dense model. And it basically says that if we satisfy these conditions, we can show that ensemble classifier model is actually epsilon prime robust, where epsilon prime is greater than another epsilon that is greater than 0. So we have a corollary, which is that a linear MoLEx model is actually more robust than a sequential model. And I think this is quite intuitive because we showed that MoLEx was an ensemble, and the sequential model, which is basically just the dense model, should always be one of the base models in our MoLEx model. So yeah, this is our intuition behind this theorem. All right, so now let's move on to our experimental results. And we show that on glue tasks, we train a MoLEx model and we compare it to if we just fine-tune the dense model with LoRa. So I think we need to keep in mind that also when we fine-tune our MoLEx model, we also use LoRa to fine-tune it. So the only difference between, let's say, a dense model with LoRa and a MoLEx model with LoRa is that we change the structure of the model by adding the router and routing it to different layer experts. But we do see that if we reuse these layers, there's actually an improvement on glue tasks, on almost all glue tasks, actually. Yeah. And yeah, so I think it's pretty good. However, on generation task, which is the end-to-end generation task, we do have some improvement, but not across all metrics. Yeah, I'm not too sure why, actually. But yeah, there's some improvement. So I think this shows us that reusing layers in a model can actually still boost performance, even though we're using like the same number of parameters as just a pre-trained dense model.
Yeah, thank you so much for the talk. I was wondering if I saw correctly, the models that you tested are really small. So do you think it scales up? I mean, I'm wondering if it's just a matter of just not having enough capacity to learn the task, because it seems like most of the models were less than 1 million parameters.
Yeah, you're right, actually.
So, and also there is the difference between the results just didn't seem really significant to me. It's like 0.2.
Yeah, yeah. So you're right in the sense that in the paper, in the main text of the paper, we do only have quite small models. But during the the rebuttal time, we actually did add some large language models. Well, we added Llama 3.1b, and we do still see improvement on, I think we tested it on maybe, I can't exactly remember what data set we tested on, but we do have some results on that in the appendix of our paper. Yeah, so it does scale up.
I have questions about do you have any insights or guesses in terms of if you deploy it in real world, and how would the parallelism strategies or the speed performance be affected compared to maybe dense models?
Yeah, actually, that's a good question. So we can notice that like similar to the mixture experts, we can actually parallelize the processing by the layers U1 and let's say UT minus 1 here. So the two different layers can be processed in parallel because we're taking the same input and we're just choosing two different layers in the model to process. So I think the compute will be kind of the same, similar to a dense model because we can do those in parallel. But the things that could change is that we can no longer use like a static computational graph because of the router, and we do not know which layer that will be chosen by the input to be routed to. So in that sense, we have to have a dynamic computational graph. And also the KV cache is affected because again, we do not know which layer that we will route the input to. So we can only maintain the KV cache for the dense model, and then the output or the KV from whichever layer we route to will be different every time. So we cannot maintain that. And so I think some efficiency is lost there as well. Yeah, but that's a good question.
I want to ask, do you identify any patterns from the trained router? Like what does the routing mechanism usually ended up learn? And what is the top K, the number of K used for the router? And do you route backward as well, only forward after layers?
Yeah, that's also a good question. So basically, we allow our input to be routed to any layer. So we can also go backwards. But in the original, the first time I implemented this, I didn't use any load balancing laws, which actually I realized was a critical part of implementing this model. Because if we do not use the load balancing laws, we will always choose, I think usually we'll choose like the next layer or the next two layers only. So within like the layer that we are at, +1 +2. So if we use the load balancing laws, we spread that out more among all the layers, but we rarely choose a layer that is earlier than the current layer that we're at. And, oh right, the K value, we use top one. Yeah, just for efficiency, I guess, yeah.
Maybe I have one question. Do you use one router with the same set of parameters for all the decision, or will you think it's better to have different router for different part of the networks since it's different input features?
Yes. Okay. So we also did experiment with that. So basically, for most of the tasks, we use one router to be shared among all the layers. But there are some tasks that I think could be more difficult to for the model to learn. And on that, we do use individual routers, and we see a performance improvement. So I think maybe if you use individual routers, it could be better, but I just want to minimize the total parameters that we need to train. Yeah.
This seems to be very interestingly connected to like these adaptive compute reentrant methods, right?
Yeah, like dynamic computing.
Like dynamic computing, right?
Yeah.
Because you can basically reroute back to an earlier layer and redo it again.
Right.
Which makes me think maybe some sort of reasoning type data set might be an interesting place to actually evaluate this to see whether you have, even if you don't improve your normal language modeling generation losses, but your reasoning performance might be more impacted by being able to have a reentrant.
Yeah, actually, yeah, that's a good idea. And I saw a paper that also did like the, deep thinking where they reuse the same layer over. So I feel like we should have included that as one of the possibilities. And so yeah, that could be a good way to improve it.
So how is the even routing to previous layers possible? Because previous computation has already been executed and you're routing back to previous layers. So how does that actually work?
I just send the input to the layer, like the earlier. So it's just when you have layers in a model, it's just kind of like a list of layers. So I just choose that one and then I just send it to the early layer.
Okay, I guess I'll just look into details.
Okay, sure.